Welcome, Mindsetters, to grade 11 science. You know what? I'm actually here with Bruce. It's my first time working together with him, and I'm excited, and I hope you guys are excited for the lesson. Bruce, what are we going to be doing today?
Ty, what we're going to be doing today is going to be energy and looking at chemical reactions and the energetics that are associated with chemical reactions. And we're going to be looking at how we actually look at bonds, chemical bonds breaking, new chemical bonds forming. Quite an exciting lesson for today.
Right, awesome. Guys, so you heard the man. Make sure you got your notepads out, your pens, and you're making notes. Guys, I cannot stress this enough. Make sure you guys go onto the page, chat to us, talk to us, let us know what you're thinking. If you're lost anywhere, if you need help, go to the page. It's www.facebook.com/learnextra. So guys, you know what? I just want to say a quick thank you to Liberty, and make sure you come back after this break. See ya. Welcome back, Mindsetters, to this grade 11 lesson on Learn Extra. I hope you guys are excited. I hope you guys are ready. I hope you guys have gotten your pens, your pads out, you're making notes. You know, I always tell you, every show, pens, pads, make notes. So you know what, Bruce? I think you can take it away from here.
Can I take it away, Tan? Great, guys. Welcome to the show, guys. It's good to be back. I've been on holiday for the last couple of weeks. And thanks very much to, I think, Phil and Tracy who've been helping me and standing in. But now I'm back, and what I'm going to be kicking off today with is looking at a section entitled Energy and Chemical Change in Chemical Reactions. Now, I'm not too sure how many grade 11s were actually watching the grade 10 show that Tracy did earlier. But Tracy was looking at writing chemical formulae and also looking at balancing of chemical equations. Now, when we've got chemical equations, we talked about our reactants and we talked about our products. What we're going to be looking at in this lesson now is how these reactants react to form the products and the energy that is associated within that system to actually change reactants into products. And that's going to be our main focus. Now, hopefully, guys, you'll find this a really interesting concept. I think it's quite simple if we just follow and learn a couple of very, very basic rules, and I'll just run through a bit of that theory with you. So if we have a look at our first point, the important thing to remember, guys, is that all chemical reactions involve energy changes. Okay, a chemical reaction does not happen unless we have energy within that system. Okay, now the other important thing is that the energy changes that take place within that chemical reaction involve either an increase or a decrease in the overall energy of the system. Now, I'm sure, guys, that you've looked at chemical reactions back at your schools, and your teacher might have added a chemical to some water or put two different chemicals together, and you might have actually felt the test tube or the container in which the reaction was taking place. And you might have said, wow, the container's got quite warm, or wow, the container's gone quite cold. Well, if the container heats up, warms up, or if it cools down, then we have got an energy change within that system. And if it heats up, we've got an increase in energy, and if it cools down, we've got a decrease in energy. And that's exactly, I just want to get my pen out so I can just do some notes as we go along. That's exactly what I'm trying to say over here. When we talk about energy changes either causing an increase or a decrease in the overall energy of the system. The next important point that I've got here for you guys is we can talk about the increase or decrease of the temperature of the system. Now, guys, why actually talk about temperature? And I'm going to put a reminder, because we did chat about this when we looked at gas laws early on in the term, is that remember that the temperature is a measure of the average kinetic energy of the particles in the system. So if we have a chemical reaction, and the energy increases in the system, then our temperature is going to increase as well, because our temperature measures the average kinetic energy of the particles within that system. So guys, there are a couple of basic ground rules that we're going to kick off with when we look at this section. Chemical reactions involve energy. Okay, the energy in the system can either increase or decrease. Okay, and that's going to affect the temperature in the system. Either temperature will increase or the temperature will drop. Okay, right. So with those basic rules down, we can now start looking at a few more of the more important things associated with this. And the first question is, what causes the energy changes in chemical reactions? What happens, guys? Energy just arrived there by magic? How does it all work? Does the chemical reaction take place all by itself, or are there some other important basics that we need to have a look at? Well, the important thing is as I've stated in my first little paragraph there, it says when a chemical reaction occurs, the bonds between the reacting particles will break, and the bonds between the new product particles will form. So guys, there are two important things that have to take place in a chemical reaction. Reactant particles, the bonds have to break, and when we form new particles, we are forming new bonds. Okay, those are the important things there. And this little statement over here is probably one of the most important little statements for understanding now how a chemical reaction works, and will allow you to understand the energetics that takes place. Old bonds will break and new bonds will form. Okay, hopefully everyone's got that. Now, let's talk about this a little bit more. And I said here, consider the following example. And I've put a very simple reaction, a very familiar reaction to all of you, which is the reaction of hydrogen and oxygen to form water. Please notice, and again, just going back to what grade 10 did with the balancing, notice we got two hydrogen molecules reacting with one oxygen molecule to produce two water molecules. We have got a balanced reaction. But what I want to do in the space below, okay, I'm just going to get a little bit more space here, is have a look now and write this out in a more careful form so you can actually see how the bonds actually are involved here. So if I take a hydrogen molecule, we all know that if I write down the hydrogen molecule in the Cooper notation, the two hydrogen atoms have formed a single bond between each other to form the hydrogen molecule. And therefore, in the Cooper notation, we represent the bond as a single line. I've got two of these hydrogens, like that, so I can draw two hydrogen molecules like that. I've got one oxygen. Now, oxygen, we know, is a diatomic molecule, and it's got double bonds between the oxygen atoms to form the oxygen molecule. Water, we know as H2O. And if I have to draw the water molecule out like that, can you see now I've drawn the oxygen-hydrogen bonds. Okay, there's your H2O, and I've got two of them. So I've drawn out to show you all the different bonds that are now going to be present in the reaction. These are our reactant molecules. Okay? Now, our reactant molecules are the molecules that are going to react together, and therefore they represent the old bonds breaking. So what's going to have to happen is that these old bonds, the bonds between hydrogen over here and the bonds between the oxygen molecule over there, they have to break. So what's going to have to happen, whoops, let's get another color, is that they're going to have to break. And I'm showing this line now to represent the bonds breaking. Now what happens, we have a recombination, okay, of the atoms to form the water. Now, the recombination of the atoms are now going to be a hydrogen bonding with an oxygen, another hydrogen bonding with an oxygen like that. So we've got new bonds. So those represent the new bonds that are going to form. And there now are the, whoops, see, just moved over there. Let's just go back. Okay, there now are the new bonds that are formed when we make the water molecule. It's the same over here. That hydrogen will form a new bond with that oxygen. That hydrogen will form a new bond with that oxygen. And then now, guys, whoopsie, sorry, it's just jumping around a little bit. There now is another oxygen-hydrogen bond. So there, guys, are our new bonds, okay? And our new bonds are our products. And that, guys, is the very simple basics of how we get reactants forming products. Breaking old bonds and forming new ones. But guys, what's the important thing about this? Well, they are not just going to happen by magic. We have to have a certain amount of energy in the system. Whoopsie. Let's bring this down. We are going to have a certain amount of energy in the system. And that energy has to be enough to break the old bonds. It has to be enough to break the old bonds. And that energy is what we call our bond energy. I'll just underline it over here. That's called our bond energy. And the bond energy is the measure of the strength of a chemical bond. So in other words, when we have these these atoms bonded together, they want to stay bonded. But to break the bond, we have to put energy in. And that energy will eventually break it. And therefore, we call it our bond energy. And the amount of bond energy is going to be relative to the strength of the bond. So, for example, if I've got a hydrogen-hydrogen bond over there, can you see now that the bond energy that's required to break that hydrogen-hydrogen bond is 436 kilojoules. Remember, guys, it's measured in kilojoules. So in other words, 436,000 joules of energy, which is quite a lot of energy because that bond is nice and strong, and therefore to break it, we've got to put things in to pull it apart. And therefore we call it the bond energy. Now, if you notice, I've got some other bond energies for you. Let's give it a little bit more like that. I've got the oxygen-oxygen bond energy slightly bigger at 495 kilojoules, and the hydrogen-oxygen bond energy is 463. Okay, I'll talk a little bit more about the hydrogen-oxygen a bit later, but I want to concentrate on those two at the moment. Those are the two that are going to be breaking. These are the old bonds, okay, or represent the energies of the old bonds. So in other words, they are going to break. So once I've put in 436 kilojoules of energy into the system, the hydrogen molecules are going to break. The bonds between the hydrogen atoms will break. And once I put in 495 kilojoules of energy, the oxygen bonds are going to break. And guys, that represents both those bonds. Not each bond is 495. Even though it's a double bond, the double bond, it's a collective total of 495 to break that. So therefore, that's how much energy we have to put into the system. Okay. Now, going back slightly, we spoke about bond energy. I've also mentioned our bond strength, and that's the relative amount of bond energy absorbed or released to either break or form a chemical bond. So our bond strength is directly proportional to our bond energy. A larger or bigger bond energy, a much stronger bond. A smaller bond energy, a much weaker bond. Okay. Now, the other important thing is they talk about absorbed, or released. Okay. Absorbed or released. Now, when we break the bonds, we have to absorb energy. The system must absorb the energy into itself. Okay? And once it's got enough energy, according to the relative bond energies, then we will get our bonds to break. However, the other important thing is that we also have energy being released when we form a bond. Okay, so we absorb energy to break, and when the new bonds form, and we'll go back up to my little diagram over here, when we form our new bonds over there, we will have a release of energy. Okay, guys, very important, because a lot of people forget about. They say, well, it's great, we can absorb this energy, but then when we form the new bonds, we're going to have energy being released. And that is why we must also, when we look at these reactions, we've got to look at now the new bonds as well. And that's the new bond. Okay? Because the hydrogen-oxygen bond making water is going to represent my new bonds. And therefore, this bond energy there, 463 kilojoules, is going to represent the amount of energy released per hydrogen-oxygen bond into the system. So guys, what have we got? Let's just quickly summarize this first part of the lesson. We've got a chemical reaction. Okay, we've got bonds between the reacting particles and bond between the product particles. To break the bonds of the reacting particles, we must put energy into the system so that those particles absorb the energy and break. Now what happens is when they reform and they recombine to make our products, over here, our new bonds are being formed, we will get a release of energy. Energy is being released. And the important thing, guys, is that the bond energy is exactly the same for the energy that's absorbed as well as the energy that's being released. So, if I've got a hydrogen-oxygen bond energy of 463 kilojoules, that would be the same amount of energy that would be needed to be absorbed to break that bond, as well as the energy released when that new bond has been formed. Okay, and that, guys, is how we're going to take this. And that, hopefully, we understand now a little bit better about how energy works into that situation. Tyz, any questions have come through at this stage?
Not yet, just besides, Bruce, we're loving the show.
Oh, great. Well, guys, I'm hoping that makes life a little bit easier and a little bit simpler for you. What we're going to have a look at after the short break, which is coming up, we're going to actually start having a look at now how we put these all together. Now we're going to look at what we call calculations or thermocalculations. Thermo simply meaning heat energy. And we're going to look at now how we use these numbers, these bond energy values, to predict what type of reaction we are going to get. And we call those reactions either our exothermic or our endothermic reactions. And I'm sure those are words that hopefully will not be too unfamiliar to you guys. So I think, Ty, I think we can take a break, and then I'll come back and I'll do this calculation for the guys back at home.
Awesome, awesome.
Great.
As Bruce said, guys, we're going to take a little break, but doesn't mean you switch off. Make sure you come back, you get your notepads, you get your papers, and you're writing notes, guys. Please, 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 write notes. And guys, again, keep chatting on the page, talk to each other, help each other out. That's why the page is there. But for now, see you after this break. Welcome back, Mindsetters. I hope you had a nice little break. Make sure that you've gotten something to drink, something to eat. If you haven't, it's okay. It's okay. This means you're going to be a little low on fuel, but please, please make sure you're paying attention, because I'm going to hand over to Bruce now, who's going to take over the rest of the show. Bruce,
great time. Thank you very much. Guys, welcome back to the show. And as I said just before the short break, I'm going to have a look at a concept called exothermic and endothermic chemical reactions. Okay. Now, guys, I'm just introducing more terminology now, and this terminology is directly related to the whole concept of energy within a chemical reaction. Okay, so we're going to look at some scenarios, some different situations, some different chemical reactions, and we're going to have a look at now how we actually start to do some calculations to predict whether we have an exothermic or an endothermic chemical reaction, and then look at how we define what an exothermic reaction is and how we define what an endothermic reaction is. Okay, so guys, we're going to look at our first situation, and it says in some reactions, the energy released on new bond formation is greater than the energy absorbed to break the old bonds in the reactants. Okay, now, how is this possible? Well, guys, we must remember that we are absorbing energy to break the old bonds, and we are releasing energy to make the new bonds. It doesn't say anything that the amount of energy absorbed must be equal to the amount of energy released. Nothing saying that, because we are forming new products. New products are going to have their own bond energies when we have those new bond formations. So we can well get a situation where we find that more energy is being released on new bond formation compared to energy being absorbed when we break the old bonds. So what I'm going to have a look at now is a little calculation, okay? And my example that I've got here is that exact same example that we looked at earlier, where we've got hydrogen and oxygen reacting to form water. There I've put down, to remind myself my relative bond energies. Remembering those bond energies, that's the amount of energy needed to break a bond, or the amount of energy that's going to be released on new bond formation. So how do we go about it? Well, guys, it's very, very simple. What we do is that we simply write down, or just draw out, my bonds, or my molecules, so I'd rather say showing my bonds, just like I did earlier. And I'm going to be drawing my products over here, which is my water molecule. And I think at this stage, everyone, whoops, that's not a very nice looking water molecule, is it? Right, so let's give that one a little bit of a rub out. And let's go back. And let's draw a better looking oxygen. And there now, guys, I've drawn out my reactants and my products, showing my bonds. Guys, what do we say over here? We've got 2 hydrogen molecules that are going to be broken. Okay, the bonds are going to be broken. Now, each one has 436 kilojoules. So it'll be 436 multiplied by 2, because we have got 2 hydrogens, 2 bonds being broken. Plus, now my oxygen is 495, okay? There's only one of them, okay? It's only one oxygen molecule in the reaction. Remember, guys, and I said earlier that 495 is for both those bonds being broken. They're not 495 each, eh? So just be careful on that. And what we can do now is that we can total up my bond energy, and I've just done it over here quickly for you guys. This works out to be 872 kilojoules. I'm not going to put my units in just yet. We'll do that at the end. That's going to be 495, and therefore my total energy required to break the bonds is going to be 1,367 kilojoules. That's how much energy is going to be needed to break the bonds. Okay. Now, let's have a look at our bonds that are being formed, my water molecules. You'll notice now we've got hydrogen-oxygen bonds. We've only got hydrogen-oxygen bonds in this particular example. But how many hydrogen-oxygen bonds do we have? We've got 1, 2, 3, and 4. Do you guys see that? Show you again. 1, 2, 3, and 4. So therefore, my energy released on new bond formation must be 463 multiplied by, whoopsie, I nearly wrote 2 because I wasn't concentrating, 463 multiplied by 4, which is going to give me a total of 1,852 kilojoules of energy. So guys, there's a perfect example to show you that the amount of energy absorbed to break the old bonds is not going to be equal to the amount of energy released on new bond formation. Therefore, we can see clearly as well, we have got much more energy that's being released on new bond formation that was absorbed initially. So, where does this take us to now? Now that we've done that little calculation. Well, as I've stated here, it can be clearly seen that the amount of energy released on formation of water is greater than the total energy required to break the bonds between hydrogen and oxygen. We've just spoken about that. Now, what is important is this statement over here. We are able to find the difference between those two energies. In other words, the difference between the amount of energy required to break the bonds compared to the amount of energy required or should I say, amount of energy released to form the new bonds. And we call this difference in energy the heat of the reaction, or the other word we use is enthalpy. Okay, and I'm going to explain both words to you guys very carefully. Okay, the heat of the reaction, all right, is basically going to be calculated by a very simple little formula. By the way, this symbol over there, delta H, that is the symbol for the heat of the reaction. And I think the symbol H standing for heat, okay, and we all should know that heat is a form of energy. Delta simply means a change in. The change in energy, the change in heat, is the difference between the energy absorbed by the reactants and the energy released by the product. So it's energy absorbed by reactants minus energy released by the products. Okay. Therefore, now we've got our symbol, and I hope we've got we understand our symbol there. I can just do this calculation for you guys. So what have we got? Well, let's put it in here. Well, energy absorbed by the reactants was 1,367 kilojoules. The energy released by the products was 1,852 kilojoules. And can you see now that my delta H works out to be minus 485 kilojoules? Okay. Now, significantly, do you notice that we have got a negative answer? Minus 485 kilojoules. This, guys, is very, very important because that negative sign is actually telling us a huge amount of information about this chemical reaction. What it's telling us is that we have got an excess of 485 kilojoules of energy that the reaction has produced. Now, if we've got an excess of energy, where is that energy going? Well, that energy is going out the reaction. Okay. And in what form is that energy? Well, that is in the form of heat. It's heat energy. So therefore, when you feel a chemical reaction, and that chemical reaction is warm, we know that we have got energy being given off, excess energy being given off from the chemical reaction itself. Guys, the other point that I want to make is that that excess, right, is not, and this is where a lot of people make the mistake, and I'm going to make a little circle that excess is not due to the energy released by the products. Okay. It's not due to that energy. It's not the 1,852. It's the excess when we actually do the little calculation, when we subtract the energy released by the products by the energy that was originally absorbed. And therefore, this 485 is actually what you're going to feel in that particular type of reaction. Now, if anyone has done this reaction in your classroom, and I hope if it has been done, hopefully it was done under the supervision of your teacher, that hydrogen and oxygen combine explosively. Okay. Now, why is it explosive? Well, the reason why it's explosive is because we've got so much energy being given off. It's been given off very quickly, and there's a lot of it. 485 kilojoules of energy is a fair amount of energy. And therefore, there's so much heat energy given off, we actually interpret it as an explosion, which means then that we've also got heat and sound energy that's being given off. Okay. Although we don't change any of the symbols, okay, heat energy, sound energy, it's still energy, guys, so therefore we still keep exactly the same symbols in there. Now, what does this all mean? Well, we've spoken about it. The value of the enthalpy, or heat of reaction, is minus 485 kilojoules. The value is negative. We've spoken about that. And what does that mean? It means that the reaction is exothermic. An exothermic chemical reaction is a reaction that will release energy, or release an excess amount of energy from the chemical reaction, which we will interpret as either heat, or in more extreme cases, we will get sound energy as well. Okay. And that's now where we get to ourselves to a definition of what an exothermic reaction is. An exothermic reaction is a chemical reaction where more energy is released on product formation than is absorbed in the breaking of bonds between the reactants. In other words, the heat of the reaction, or what we call the enthalpy of the reaction, is a negative value. It's excess energy that is being released. Okay. Now, we've been using this word enthalpy, okay, as an alternative word for heat of reaction. Let's just make 100% sure that we do understand what we mean by the term enthalpy. And what I've done right at the bottom of the slide, I have put in a short little explanation for the term enthalpy. It's the measure of the heat content of a chemical system at a specific pressure. Okay, so when we have 1,367 kilojoules of energy being absorbed, and when we have 1,852 kilojoules of energy being released on product formation, therefore we have got a difference of 485. It's a negative value, which means it's been given out. Therefore, that is going to be the heat content. So the heat content is delta H of minus 485 kilojoules, means that is the excess. The heat content will represent, in this case, our excess amount of energy. Okay. So guys, I hope you're comfortable with that concept of heat of reaction and the concept of enthalpy. It's exactly the same thing, but as long as we know exactly what we understand by those terms. Okay. So guys, that is now an exothermic reaction. What about an endothermic reaction? Well, let me pop over to the next slide. And let's look at the endothermic reaction, where I say now that in some reactions, the energy released on new bond formation is less than the energy absorbed to break the old bonds of the reactants. Okay, so sometimes when we release energy on new bond formation, it's actually less than the amount of energy that was originally absorbed. So let's have a look at an example of this. And here is an example where we've got hydrogen and iodine to make a molecule called hydrogen iodide. And you can see now that we've got one part of hydrogen and one part of iodine to form two parts of hydrogen iodide. So let's have a look now and let's do the calculation associated with the chemistry and the energy within the reaction. Hydrogen, 436, as we had earlier. And I've looked up and given you the data for the iodine bond. Remember, your hydrogen is simply going to be HH. Iodine will be II, single bonds between them. And my hydrogen iodide is simply going to be HI, but we have got two of them. Okay, so what have we got? We've got 436 times 1 for hydrogens. Only one hydrogen molecule breaks. Iodine, 181 kilojoules of energy, and there's only one of them, okay? Which now, if we simply add them up together, 436 plus 181 gives me 617 kilojoules, okay? That's how much energy was required to be absorbed to break those particular bonds. Now we form our hydrogen iodide. Well, hydrogen iodide is 299 kilojoules of energy per bond formed. Okay, that's the bond energy of hydrogen and iodine. So it's going to be 299, but we've got two of them, okay, because we've got two HIs, which gives me a total of 598 kilojoules. Guys, can you see now that we've got something different than compared to the previous example? We have now got less energy being given off than was absorbed by the reactants to break the bonds. So let's do our calculation. Okay, there it is. We spoke about it. My heat of reaction. So that's now going to be energy absorbed by reactants is going to be 617 minus the energy released by the product, which is 598. And my delta H now works out to be plus 19 kilojoules. It's a positive value. Sorry, it got a little bit squashed in there. But do you notice, guys, we now get a positive value. Now, whoopsie, that should be, sorry, my bad, I'll just change that. That should be plus 19 kilojoules. The value is positive. Now, what does that mean? Well, if it's positive, it simply means that my reaction is endothermic. Okay, and what do we mean by an endothermic reaction? It's a chemical reaction where less energy is released on product formation than is absorbed in breaking the bonds between the reactants. The heat of the reaction, or the enthalpy, is a positive value. So guys, that in a nutshell is how we can predict and calculate whether a chemical reaction is going to be exothermic or endothermic. Time to take a break?
I think so.
Great.
Good. So guys, I hope you guys have learned a lot right now and you've been paying attention. Because guys, you need to keep chatting to me on the page so I can get those questions. Right now I'm still collecting them. But guys, make sure you keep chatting on the page, talk to each other, help each other out. That's what the page is there for. But for now, we're going to take a break. See you soon. Welcome back, guys, to this grade 11 science session. Guys, make sure you keep chatting on the page. I keep telling you, and I hope you guys are making notes at home. You got your pens and your pads out. You're writing this down because Bruce is here, and he's supposed to be teaching you guys. So, guys, he's not just doing this for nothing. It's for you. But Bruce, actually, before we go on, I've got a question from Sipo Setu here. And she says, hey, sorry, but I don't understand. Isn't it the unit of enthalpy, kilojoules per mole, instead of just kilojoules?
Okay, right. That actually is quite correct. But what I've been doing at the moment, I've just trying to be showing you guys that we have got an energy differential. The actual unit, and I'll put up on a blank screen over here. The actual unit for the delta H is a kilojoule per mole. Okay, now that brings in a lot more complication when it comes down to the actual reactions themselves. That is something that's probably going to be looked at in another lesson, okay, where we actually look at the number of moles that are present in the products, okay, and the number of moles that are present in the reactants, okay. At this stage, all I was trying to do is to show you guys that we've got differences in energy. Once we go into kilojoules per mole, we're going into a more difficult type of situation. But we will find that we actually do refine the unit of heat of reaction, or the unit of enthalpy, to kilojoules per mole. And therefore, we will talk about those in a bit more of a context once we understand these reactions more fully. And I think we can look at that at another time.
Yeah,
okay.
Awesome. And then I've got another one from Alan. He or she, I'm not sure, there's a girl in the picture, so I'm not sure if Alan's a girl or a guy, sorry. But what type of reaction is it when sodium hydrogen carbonate reacts with the hydrochloric acid?
Okay, sodium hydrogen carbonate is NaHCO3, and that reacts with hydrogen carbonate. Hydrochloric acid. Now, sodium hydrogen carbonate, guys, a lot of you guys might recognize the formula, and that's very simply common baking soda. And when hydrochloric acid reacts with sodium hydrogen carbonate, we form sodium chloride, we form carbon dioxide, and we form water. Okay. Now, that carbon dioxide, just a quick little digress here, that's the carbon dioxide that bubbles off, and why we use it in baking soda is that the bubbles now lift the dough, that lifts the cake mixture, and that's what makes your cakes all nice and light and fluffy, is because you've got carbon dioxide which is actually bubbling off from this reaction. Okay, but guys, what's important here is that when we look at this reaction, there's nothing to tell us whether this reaction is an exothermic or an endothermic reaction. The only way we can work this one out is that if they give us some information. And if they put this down, delta H is equal to a positive value. If they give you delta H as a positive, then it is an endothermic reaction. Or if they give you, sorry, let's just extend the page a bit. If they give you delta H is equal to a negative value, like that, then it's an exothermic reaction. So what you'll find is that on the right-hand side of a chemical equation, they will give you one or the other type of symbol. They can either tell you it's positive, they may give you an actual value, but they must say plus 150 kilojoules. They must say minus 175 kilojoules. They have to give you some indication. Only then and only then are you able to realize that that reaction is either exo or endothermic based on giving this. If you do it practically, though, I must admit, sodium hydrogen carbonate, when it reacts with hydrochloric acid, you go and feel that reaction. It's quite warm. So you'll find now that your reaction is actually going to be exothermic. It's actually quite a warm reaction. So when they write this down, they should actually give you delta H value being negative to tell you that it's exothermic.
All
Okay.
right. I think that was about it for now.
Is that about it for now?
Yeah.
Okay. So we've got about 10 minutes, guys. So what I'm going to do in the next 10 minutes is basically have a look at what we call, whoops, what happened there? We just jumped a page. And we're going to have a look at how we can represent exo and endothermic reactions. They're called energy profiles. And all an energy profile is a graph, a graphical representation of showing the energy that takes, or the energy movements, or the energy transfers that take place in the chemical reaction. It's just another way of showing you. Instead of doing the calculations, we can show you using an energy profile. So, I'm going to have a look at an exothermic graph, and all we do is that we draw a set of axes, and we put a label on the y-axis, we put there delta EP. That stands for the change in energy. Okay? And basically what we've got here is a time axis. Okay? And that time axis, it's so quick, we don't even actually have we don't use a stopwatch or anything like that. And often we'll find that they will talk about something called a reaction coordinate. A reaction coordinate. All a reaction coordinate, it's a time scale, but it means it's going so quickly that there's no measurable values. So we just say as the reaction progresses. Okay. Now, if we look at an exothermic graph, we always start off with our reactants with a certain amount of energy at that particular point. So therefore now, I'm going to call that EP1. Okay? And that's now the energy of the reaction before the reaction started. Now, to start the reaction, it's got to absorb energy. So what actually happens is that the graph actually, the profile of the graph actually goes up. The energy gets absorbed until we reach a point at the top here called an activated complex. It's called an activated complex. So what's happening now is that can you see now, guys, that the energy is going up? In other words, it's absorbing energy. So the energy within the system goes up because it's absorbing. And as it's absorbing, it's getting enough energy to break those old bonds. Okay? At this point here, the activated complex, this is when our old bonds break. Okay? And our new bonds form. Okay, that is the point when the old bonds break and the new bonds form. And what happens then? It's now got enough energy in the system, we have absorbed it, the bonds break, and now we release the energy as the new bonds form. And therefore, if we release the energy, the profile will drop. And you will end up getting a profile that looks something like that. Now, you'll notice now that represents the energy of the reactants. If I take this line across like this represents, I'm going to call that EP2, that represents the energy of the products. And can you see now that we have got a large amount of energy being given off? That's the energy released on product formation. Okay? This over here is the energy, if I take it to the top to the activated complex, that represents the energy which is now going to be absorbed to break the old bonds. And therefore, can you see now that we've got more energy being released than was absorbed by the reactants? And remember what we said about exothermic reactions? Exothermic reactions basically are reactions when more energy is released than was absorbed by the reactants. And this is now a classic style of how we show an exothermic graph. Can you see now that the starting amount of energy of the reactants was actually higher than the finishing amount of energy of the product? Why? Because more energy was actually released. Now, this energy over here carries a special name. It's called the activation energy. Okay, and I want to spend a little bit of time talking about this activation energy. The activation energy basically is that amount of energy that now needs to be absorbed to reach our activated complex. Only at the activated complex will old bonds break and new bonds form. They won't start breaking at any other point around here. Okay, so therefore, at this point, and in fact, I'm going to make this point a little bit more clearer there. There we go. At this point there it is, right at the top. Okay, right at the top. There's my activated complex. So to get from my starting energy, which is the natural energy in the system, it's got to absorb the energy, so it gains activation energy, reaches the critical point where we can say, right, we've got enough energy according to our bond energies, our bond strengths. We now can start to break the old bonds. There we form the activated complex. And the symbol for our activation energy is given with an E with a subscript A, which means energy of activation. Okay, and I've actually spoken about the energy of activation over here as the minimum amount of energy needed in the system before a chemical reaction can take place. So in other words, we must absorb energy in the system to reach that activated complex where the old bonds break and new bonds formed. It's the minimum amount required. Now, we can talk about our activated complex again. The chemical complex formed where there's enough energy to have old bonds breaking and new bonds forming, and another name for it, which I just want to underline here for you guys, it's called a transition state complex as well. Now, you can use other words, guys, okay? The most popular word is activated complex. That's why I've sort of stuck with it. But often you'll hear people talk about a transition state. What does transition mean? Transition means changing from one to the other. It's changing from reactants into products, transition state complex. Okay, now, if we go back to our diagram, where is our heat of reaction? Where is our enthalpy? How do we work that out? Well, remember guys, it's the difference between the amount of energy absorbed by the reactants, the activation energy, and the amount of energy released on product formation. So therefore, that space there, that there is going to represent my delta H. That is going to be my heat of reaction. And can you see now that my heat of reaction is represented by that space, which is actually showing the energy below the starting energy of the, below the starting energy of the reactants. Why? Because the energy of the products is now much less because of all this energy that's been released out the system. And that, guys, is the exothermic reaction. Very quickly, I'm going to show you guys the endothermic reaction. Okay, what does that look like? Okay, let's just quickly show it. I'm just going to extend the page quickly over here. There we go. The endothermic is somewhat different. Okay, we're going to put our delta EP, the energy in the graph, my reaction coordinate. I'm just going to do it in shorthand because we are running out of time. It's very similar to start in that the reactants have now got the starting energy. It climbs the hill, gets to the activated complex, but however, you will notice now that it doesn't fall very far. Why not? That's because, if we have to now do on our markings, that represents the amount of energy released on new product formation. This is still my energy absorbed. That's my activation energy over there. Can you see now that less energy is being given off on product formation compared to energy being absorbed? Remember that from endothermic reactions. Now, where is my delta H? Well, my delta H is going to be there. That's my delta H. Okay. Again, the space between, let's go back to, I'll label this P for products. It's the space between my reactants, my starting energy of the reactants, and my final energy of the products. And that is why delta H will be a positive value, because we do not fall as far. We have much less energy being released on product formation. I think that's basically, all we've got time for at the moment.
Yes, I think so. So guys, I hope you guys had fun. I'm going to wrap this up quick. I just want to say a quick shout out to Jamelia. I didn't forget. And my man, Eric, I didn't forget either. Guys, hope you had fun. You guys make sure you use the page. It's for your notes. It's for everything. It's got everything there. You chat to each other, help each other out. But for me, I'm going to sign off. This is Ty. Peace.